So if you want to write the dipole moment for carbon dioxide, what we will do, we will consider here. So here you can see, I will show it like this, and here it will be shown like this. So what will happen? There are two dipoles which are acting. Yes, there are two dipoles which are acting, but they are equal in the magnitude, but they are opposite in direction. Both are equal in magnitude because C double bond O, C is a double bond O. Both are equal in magnitude. Their value will be same, but they are opposite in direction. Therefore, what will be the net dipole moment? The net dipole moment will be 0. Yes, both of them cancel out. Yes, they will cancel out during vector addition and the net dipole moment becomes 0. Let us consider one more molecule. Like let me say we will take, this was second example what I had discussed, we will take a BF3 molecule. Yes, I will represent BF3 like this. So this is having say a trigonal structure. So I will write BF3 molecule. Now you can see, you can judge out how to write the dipole moment. See, between these two, fluorine is more electronegative. Therefore, I will show the dipole moment like this, towards fluorine, arrow towards fluorine. Here also the arrow is towards fluorine. Here also the arrow is towards fluorine atom, right? Because fluorine is more electronegative when we consider all of them. Fluorine is more electronegative, right? How many dipoles are there? Actually, there are 3 dipoles. 3 BF dipoles are present. But all the 3 BF dipoles, you can see, they are all equal in magnitude, but they are opposite in direction. So the net dipole moment will be what? It will be 0 again. Yes, the net dipole moment will be 0. One more molecule you can consider. CH4. CH4. It is called methane molecule. Yes, if you just look at the structure of methane, it is something like this, which we call it as a tetrahedral structure between carbon and hydrogen, which is more electronegative. Carbon is more electronegative. So I will show it like this, correct? Here, which is more electronegative? Carbon is more electronegative towards. Here also, carbon is more electronegative. Here also, carbon is more electronegative. Getting my point? So these are all what? These are all symmetrical. I call them. They are all symmetrical. Polyatomic molecules. So if you have symmetrical, see everywhere symmetry is there. If you have symmetrical polyatomic molecules, though there are presence of more than one dipoles, yes, they are not polar. They are not polar. Because polarity is measured by what? It is measured by dipole moment. And they will not cancel, they will all cancel out each other. So they do not have any value of dipole moment, and mu is 0 for symmetrical polyatomic molecules. Now, what if I consider unsymmetrical polyatomic molecules? Unsymmetrical polyatomic molecules. Okay, let us consider simple example, water. Okay, I can write water like this. Yes, don't forget oxygen is having 2 lone pairs. Okay, how do we show dipole? Oxygen is more electronegative, so there is some dipole here towards oxygen. This is also towards oxygen, right? Yes, and because of presence of the 2 lone pairs, they will add to the resultant dipole. They will also add to the resultant. Both are in same directions. They are not in opposite directions. So they will add up. So there is resultant dipole also because of these 2 dipoles. So here the resultant dipole is because of 2 OH dipoles and 2 lone pairs. So it will have some net dipole. Therefore, I call it as polar molecule, and the net dipole moment of water molecule is 1.84 d pi. 1.84 d pi. Understanding? So both are in same direction. Along with this 2 OH dipoles, there is also dipole because of the 2 lone pairs. They will also add up to the resultant dipole. They will add up to the resultant dipole. One more example, ammonia molecule, NH3. I can write ammonia molecule like this. And you know that in ammonia molecule, there is one unbonded pair on nitrogen. Yes, so how do we show it? Here, this is shown in this direction. Nitrogen is more electronegative. Dipole moment I'll show like this. Dipole moment I'll show like this. Along with these 3 NH dipoles, there is one dipole because of lone pairs. So it will also add to the resultant dipole, and there will be some resultant dipole, and the dipole moment of ammonia is 1.46 d by 1.46 d by. Similarly, you can consider methyl chloride, CH3Cl. Yes, you can see here, carbon, 3 hydrogens, and here there is 1 chlorine. Yes, so I can explain it like this. So carbon is more electronegative, it will go here. Carbon is more electronegative, carbon is more electronegative, but here chlorine is more electronegative. So all these three minus this, you will get the net resultant dipole, and the net resultant dipole is a 1.86 d by 1.86 d by. Understanding? So symmetrical polyatomic molecules are not polar. Though polarity is there, they are not polar because dipole moment is what? Dipole moment is 0. Unsymmetrical polyatomic molecules, they are polar because they possess some resultant dipole. They do possess some resultant dipole. Yes, these are some of the examples to make you all understand. One more here, what we can understand from one more example is compare dipole moment of NH3 and dipole moment of NF3. Let us check. Nitrogen. Here hydrogens are there, and there is 1 lone pair here. Nitrogen, 3 fluorine are there, and there is lone pair. Correct? How do you explain the dipole moment? Here nitrogen is more electronegative, therefore I will show the dipole moment towards nitrogen, arrow mark pointing towards nitrogen and a positive charge towards hydrogen. Arrow mark pointing towards nitrogen and a positive charge towards hydrogen. What about NF3? Fluorine is more electronegative, so I will show the arrow mark pointing towards fluorine, positive charge towards nitrogen, pointing towards fluorine, positive charge towards hydrogen, pointing towards fluorine, positive charge towards hydrogen. In case of NH3, we know that these are the 3 dipole moments which are in same direction, and the resultant dipole is also because of this lone pair. And what is the value for NH3? It is 1.46 d by. What about NF3? Immediately we will come to the conclusion that NF3, all the dipoles, they are present, they are equal in magnitude, but they are opposite in direction. So you will say the mu, that is dipole moment, is 0. No, it is not 0 because you are just observing NF dipole moments. What about this dipole? This contributes, lone pairs also contribute. So it is not equal to 0. There is some net resultant dipole for NF3 molecule, and that dipole moment for NF3 molecule is less than dipole moment of NH3. That's it. So I can say it is not 0. It is less than dipole moment of NH3. So it is less than 1.46 d by. It is less than 1.46 d by. So what is the use of this dipole moment? What is the application? We'll check out. So dipole moment we have seen here. Applications of dipole moment for determining the polarity of the molecules. Though bonds are there, though charges are present, we cannot say it is polar. So the polarity can be determined by dipole moment. Therefore, I can say dipole moment is the degree of polarity of a molecule. Yes, if it is symmetrically polar, then dipole moment will be 0. If it is unsymmetrically polar, then there will be some dipole moment. In finding the shapes of the molecules, it helps us to determine the geometry of the molecule. Geometry means what? Shape of the molecule. For example, carbon dioxide, carbon disulfide, CO2, CS2. These molecules are having linear shape. Yes, CO2. I can show you here. We have discussed also this concept. CO2. Even we have CS2. Both of them are having, can you see this? They are having linear shape as their dipole moments are 0. Since their dipole moments are 0, they are having linear shapes. They will cancel out each other. H2O molecule, NH3 molecule, expectedly their geometry is, their shape is tetrahedral, but their shape is not tetrahedral because they have some dipole moment. If it was tetrahedral, it would be 0. Second point, it also predicts or determines the orientation in the benzene ring. Greater the dipole moment, greater is the asymmetry. Yes or no? If there is only unsymmetrical, we can predict dipole moment. Therefore, I say greater the dipole moment, greater is the unsymmetry. Yes, so in general, we can say for benzene ring, ortho is having more dipole moment than meta, which is having more dipole moment than para. Now, what does this ortho meta para means? See, in benzene ring, if there are two substituents, we give names like this, or this can be here also, okay? And keeping this same, this bond can, one compound can be here, or it can be here also. And third one, it can be like this also. So this position, either this side or this side, it is called ortho position. This position is called meta position. This side or this side. And this position is unique. It is called para. So I call it as 1-2 position, or this side 1-6. This is 1-3 position, or this side 1-5. And this is 1-4 position, unique para position. Therefore, because of asymmetry, this is asymmetric, right? And this is more symmetry. So dipole moment of ortho is more, then meta, and then para. Para is having least dipole, or you can say since it is symmetry, it is 0 only. It is 0. Understanding? So what are the applications, or you can say what is the significance of dipole moment? It helps in predicting the shapes of the molecules. The molecules with 0 dipole moment will have linear or symmetrical geometry. Those molecules having unsymmetrical shapes will either be bent or angular. They will have different shapes. For example, NH3, it is 1.47 or 1.46 dpi. Its geometry is pyramidal. In calculating the percentage of ionic character, you can calculate the percentage of ionic character. Yes. So percentage of ionic character, I can show you the formula what we can use. To calculate the percentage of ionic character. So percentage of ionic character is given by observed dipole moment upon accurate or theoretical dipole moment into 100. You will get the percentage of ionic character. Yes, so you can even calculate the percentage of ionic character. This is a formula. Observed dipole moment divided by theoretical dipole moment into 100. You will get to know how much ionic character is there in the molecule. Now, when this dipole moment comes into context, we have certain points to understand. Okay, what are those points? Suppose I will consider we have discussed both. Okay, what all we have discussed? We have discussed about ionic compounds, and we have discussed about covalent compounds. Correct. Now, what if I want to compare? See, ionic compounds means one of the, we know what the characteristics, we know the factors affecting ionic bond formation. One should have least ionization energy, means what? Its size. The one which is having least ionization energy is a cation. So its size must be very big. Yes. And the other which should have very low, high electron gain enthalpy. Yes, that means it should have very high electron gain enthalpy. Its size should be small. So cation should be larger, anion should be smaller. Correct? What if it is opposite? If cation is small and anion is large, what will happen? The ionic character will decrease. So depending upon that, I had explained you lithium chloride, sodium chloride. Yes, chloride is same. So cation, as you move down the group, atomic size increases. So where cation is more, this is more. Therefore, I'll say NaCl is more ionic than lithium chloride. Yes or no? This was what we had seen in ionic compounds. Speaking about covalent compounds, see magnitude of polarization or increased covalent character. Where more covalent character is there? Character. Yes, it depends upon number of factors. Under that, the first factor is Fajan's rule. What does Fajan's rule says? What does Fajan's rule says? Fajan's rule has two small points. First one, smaller the size of cation. Smaller the size of cation. Yes, when a covalent, if you want to explain more covalent character, smaller the size of cation, what happens? Okay, so we'll discuss it. Smaller the size of cation, greater will be its polarizing power. That is, greater will be the covalent nature of the bond. If the size of cation is more, we know it is ionic bond, yes or no? So if the size of cation is less, if the size of cation is less or smaller the size of cation, what will happen? Greater will be its polarizing power. Greater will be its polarizing power. Now, what do we mean by polarizing power? Okay, this is cation, and let me say this is my anion. I'm taking vice versa. Okay, so smaller the size of cation and larger the size of anion. Okay, so I've done vice versa. So if the size of cation is small and size of anion is large, opposite of this. If this is the case, it is purely ionic. I am speaking in covalent compounds where covalent character is more. Okay, getting my point? Okay, fine. See, if the size of cation is less, what will happen is it will have more polarizing power, I said. Greater will be polarizing power. Means what? Means its nuclear attraction will become more. If the size of cation is small, nuclear attraction will become more. And when it approaches the anion, what will happen? Let us see what will happen. When both the ions come together, larger the size of anion, more is its polarizability power. That means more will be its power to get polarized. This will have power to polarize something, and this will have power to get polarized by someone. Yes. So what is this? Let us try to understand. This is nothing but Fajans rule. Since the size of cation is less, when both ions are approaching towards, the nuclear attraction will be more. Okay. On the other hand, since the size of anion is more, the electrons of the outermost shell, they are very far. Therefore, nuclear attraction here will be less. Are you all getting? So when this approaches, when these two ions approach each other, the nucleus of cation will only pull the electrons of anion, correct? This anion is having nucleus also, and it is having electrons also. Are you all getting? Yes, you are understanding. So it will pull the electron density only towards itself. So when it pulls the electron density only towards itself, what will happen? Only the electrons get attracted. Only the electrons get attracted like this. So this is what? This is electron density which is getting attracted towards the cation, and positive charge remains something here. So is it not, since the size of cation is small, is it not creating polarity in the anion? Is it not creating the polarity? Yes or no? Therefore, I said smaller the size of cation, greater will be its polarizing power. So it will polarize the anion by creating the charges. Yes. Larger the size of anion, more is its polarizability power. So since anion size is large, the outermost electrons, they are easily dragged by this nucleus, because this nucleus is holding those electrons loosely because the size is large. So it gets polarized very easily. It gets polarized very easily. Since it is getting polarized very easily, the electrons are coming in near the vicinity of this nucleus, and positive charge is thrown away. It's like thrown away. There is a disturbance created in the shape of this ion, and that is said to be distortion. What it is said to be? Distortion. There is distortion in the molecule. There is distortion in the shape of the molecule. Are you all getting? So smaller the size of cation, greater will be its polarizing power. Therefore, we say greater will be the covalent nature of the bond. Larger the size of anion, more is its polarizability power. Therefore, greater will be the covalent character. Greater will be the covalent character. So these are 2 points. These are the first 2 points. What is the third point? So when covalent character is more, when the size of cation is less and the size of anion is more. So I'll consider these 2 examples now. Let me say these are covalent compounds. So tell me which is having more covalent character. They are ionic only, but tell me which will have more covalent character. Just look out where size of cation is less. In this case, size of cation is less. Correct? This is cationless. Therefore, I can say lithium chloride is more covalent than sodium chloride. Understanding? Or if I give you NaCl and NaF. So which is having more covalent character? Both are ionic compounds, but there is covalent character. Which is having more covalent character? So you have to look out. So cations are same. I'll not worry. Look at anions. Which is having more size, large size of anion? This is having more large size of anion. So I can say sodium chloride is more covalent than sodium fluoride. Understanding? So this speaks about Fajans rule. Third point says larger the charge on any of the ions. So consider NaCl and MgCl2. So here Na is having plus, Mg is having plus 2. So larger the charge on either of the 2 atoms, what will happen? As the charge on the ion increases, electrostatic attraction of the cation for outer electrons of anion also increases. What will happen? Ability for forming covalent bond also increases. As the charge increases, so I can say MgCl2 is more covalent than NaCl. So this is all about Fajans rule. This is all about Fajans rule. So what does Fajans rule says? So based on Fajans rule, you can say which compound has more covalent character. So in covalent compounds, we have polar covalent compounds, non-polar covalent compounds, correct? We said polar covalent compounds are those which are where electronegativity difference is less. Non-polar covalent compounds are those where electronegativity difference is 0. In ionic compounds, which are completely polar, in ionic compounds also there is covalent character, and that covalent character is explained by Fajans rule. There are 3 rules. So how can you say which is having more covalent character? Smaller the size of cation, greater will be the polarizing part, so greater is covalent character. Second, larger the size of anion, more is its polarizability power, getting polarized. More is the covalent character. And third one, larger the charge on either of the 2 ions. As the charge on either of the 2 ions increase, covalent nature increases. So based on this, we can compare and say, based on the Fajans rule, we can say in ionic compounds, which is having more covalent character. In ionic compounds, which one has more covalent character can be said by which rule? Fajans rule. Very, very, very important rule. Yes, we can explain which one has more covalent structure, more covalent character. Yes, so if I would have given you, like for example, say, let me say sodium oxide, Na2O, and magnesium oxide, which is having more covalent character. Anions are same, I'll not worry. Cations. Look at the cations. Sodium is Na plus, Mg plus 2. Charge I am going to speak where charge is more. MgO is more covalent character than Na2O. Clear with this? Sodium, one more example I will give you. Lithium fluoride and lithium chloride. So lithium, cation is same, I'll not worry. Anion. See, anion size should be larger. As you move down the group, atomic size increases. So this is having more large size. So lithium chloride is more covalent than lithium fluoride. Are you all understanding? So this is how we speak about the more covalent character in ionic compounds. Yes, therefore, I conclude saying covalent character in ionic compounds can be explained by Fajans rule. 3 rules. What are 3 Fajans rules? First one, smaller the size of cation, More will be its polarizing power. Therefore, more is covalent character. Second point, larger the size of an ion, more will be the covalent character. Third point, larger the charge on either of the ions, more will be the covalent character. More will be the covalent character. Is that right? So this is about the Fajans rule. Covalent character in ionic compounds. And you can see here, these are some of the dipole moments. Chlorine, 0, symmetrical. CN, C2N2, 0, symmetrical. Here, there is some dipole moment because of nitrogen. So it is lone pairs on nitrogen. So it is 0.37 dpi. H2O2, hydrogen peroxide, 2.06. Ammonia, 1.84. These all molecules. This is having some net dipole. Here, net dipole is 0, no net dipole. CH2O, formaldehyde, there is some net dipole. NH3, there is some net dipole. And this is resultant dipole. It is resultant dipole. Net dipole is 0. Resultant dipole exists because of CCl bond, 0. And here also it is 0. So these are some of the explanations. In the next class, we'll discuss about valence shell electron pair repulsion theory, which is abbreviated as VSEPR. For now, practice all the concepts what I have explained. Thank you.